Hi, I'm Dr. Leslie Blankenship-Williams, and this lecture continues with the topic of control of gene expression and gene arrangement. The previous lecture focused on eukaryotes. Here, we look at how bacteria or prokaryotes do it. So prokaryotes take a more simplistic approach. Like eukaryotes, there are usually multiple genes that need to be turned on in order to achieve some outcome. For instance, let's say you're a little bacterium that's swimming along and you encounter a whole bunch of new nutrients that are plentiful and you want them, but you haven't encountered that nutrient in a long time. So you don't have the machinery available yet to transport that nutrient into the cell and then break apart that nutrient so you can make ATP or use it for parts. So if you do want to capture that nutrient and use it, you're going to have to express some genes that will help you do that. Namely, you're going to need a transporter enzyme to bring that nutrient into the cell, and then you're going to need some enzymes to break it down. So that's multiple genes that you're looking at. Transporters, probably 2 or 3 different genes, and enzymes are each going to at least be one, if not more than one gene. So where are those genes located on this single circular chromosome? Well, they're all going to be located together. So we know that eukaryotes have a tendency to spread their genes around to different chromosomes, but prokaryotes are going to put them together. So if the gene for transporting that sugar is located here, then you can bet that the genes for metabolizing that sugar are also located in that same spot. And moreover, all of those genes are going to be controlled by one master switch, and that master switch is known as an operator. The collection of genes in tandem that all go to some outcome and their single control that precedes them are collectively known as an operon. Let's take a closer look. So here I have an enlargement of an operon. This operon has only 3 genes with it. So we have hypothetical gene A, gene B, and gene C. And we presume that all of these genes would need to be expressed in order for the cell to achieve some outcome. Notice that preceding these genes, which are all located one right after another, is something called an operator. And then in front of that is something called a promoter. And these are just other regions of DNA. The operon is all of these put together. So this represents a single operon. Now, in addition, we're going to need to bring RNA polymerase into this picture because we know that gene expression is controlled at the transcriptional level. And more specifically, it's controlled by whether or not RNA polymerase is allowed to transcribe genes A, B, and C. We also learned in a prior lecture that RNA polymerase is attracted to the promoter region, and that tends to be where RNA polymerase likes to start. So let's assume that RNA polymerase comes down here to the promoter. If RNA polymerase is now allowed to move along this double-stranded DNA helix, it will transcribe genes A, B, and C. However, if RNA polymerase is somehow not allowed to move past this region, then no transcription of genes A, B, and C will happen. So unlike eukaryotes, which controlled gene expression largely by whether or not RNA polymerase was even allowed to the promoter site, in prokaryotes, RNA polymerase tends to be permitted to any promoter site. The control happens with an interaction between the operator and another molecule known as a repressor. So the operator is a section of DNA in between the promoter and the genes that need to be transcribed. The repressor is a physical, big, bulky protein usually that is attracted to this operator section. And if it sits down on the operator like so, it prevents RNA polymerase from moving downstream and transcribing genes A, B, and C. It is a physical blockade. So if we assume that my fist is RNA polymerase and RNA polymerase is running along, the repressor is literally a wall. It's like, no, can't go past, can't go past, can't go past. So if the repressor is sitting on the operator, no transcription happens. Note that the transcription of genes A, B, and C are all linked together. In other words, if the repressor is removed, so we'll just quickly remove it here, and RNA polymerase is allowed down, then gene A is going to be transcribed, gene B is going to be transcribed, and gene C is going to be transcribed. There's no picking and choosing. It's not as if you can transcribe gene A but not B and C. It is an all or nothing deal. Either all of the genes in the operon are transcribed or none of them are. And that is what we mean by the master switch. It turns out that operons come in two different designs. In other words, they use their repressor in different ways. The two designs are called inducible and repressible. Let's take a closer look at what this means. I'm going to start with the inducible operon. The word inducible suggests to turn on, like to induce delivery of a woman who is pregnant. So typically, women who are induced are not progressing in their labor and therefore delivery. And so you induce labor and delivery by adding Pitocin. In the same way, inducible operons have a default position of off. But if you give them a little something special, you can turn them on. So inducible operons are by default off. And what that means is by default, the repressor is sitting on the operator and preventing RNA polymerase from transcribing genes A, B, and C. But an inducible operon can be turned on. In other words, it can be induced. How is it induced? Well, usually there's another molecule. In this case, I have a little red dot called the signal molecule that will bind to the repressor. And when that signaling molecule binds to the repressor, it causes a conformational change in the repressor that allows the repressor to leave the operator. When the repressor leaves the operator, there is no longer a physical blockade for RNA polymerase, and RNA polymerase starts its moving downstream and doing its transcription. So again, an inducible operon is typically not experiencing gene expression. But if an appropriate signal is given, then that signaling molecule will bind to the repressor detaches from the operator, and now RNA polymerase is free to start transcribing. And that will continue to happen until the repressor rebinds the operator. So that's one design. A second way that operons can be designed is where the default position is on. And these are referred to as repressible operons. So in this case, RNA polymerase is going to keep making RNA transcripts over and over and over again until it encounters a block. Well, when would it encounter a block? Well, when the repressor binds, of course. So the term repressible has in its root repress. To repress is to minimize or to stop or to make negligible. So in other words, a repressible operon is one that can be turned off when needed. And like the other case, there's usually a signaling molecule that will bind to the repressor. And once that happens, that creates a conformational change in the repressor that makes it more attracted to the operator area. And then it binds. And now, once that blockade is in place, RNA polymerase is no longer capable of transcribing, and therefore transcription is turned off. The terms inducible and repressible can be a little bit counterintuitive when you first learn them, but think of the terms this way. Inducible, to induce. If you are inducing something, you're turning it on, like to induce a delivery is to turn on the labor and delivery so that that woman gives birth quickly and easily, hopefully. But that means that she wasn't already progressing in her labor and delivery. To induce it means to make it start, make it go faster. In other words, her default position was not giving birth, and then you had to induce it to start that process. In the same way, an operon that is classified or designed as inducible is not on by default, but you can turn it on if you need to. The term repressible can be viewed with the same lens. Repressible means to repress or turn off, but that implies that the default position is on. Now, operons are designed this way depending on the needs of the cell. Repressible operons, because their default position is on, tend to be operons that the cell needs all of the time. In other words, the cell needs those products all the time. Inducible operons are ones that typically the cell doesn't need and only needs in special circumstances. If you had to guess, which kind do you think is more common in a genome? And surprisingly, repressible operons are slightly more common. So for instance, in E. coli, it is estimated that around 60% of the operons are repressible and 40% are inducible, meaning that repressible operons are a little bit more common than inducible ones. Okay, the last lecture objective is one that you are tasked with, and that is to look up and do your own research on the lac operon, which deals with lactose, a rare sugar. And what you want to do is look at that operon and determine, is it an inducible operon or a repressible operon? All right, that's the end of our lecture. Thanks for watching.